Hey there. As you can see by looking at this, we're going to be talking about section 625 today. And the other thing you can see if you look here is this is the last section we're going to do in this chapter. So this will be it. If we were in a regular situation, you'd be having an assessment over this, but we're not doing that. As long as you've been taking notes and handing in assignments, you're going to get a good grade on this chapter. But here is the point of this chapter. What if a line does not fit the data? And we're going to look at curved best fit models. So in order to do that, I just want to take a little time to review. We did some work already this week reviewing linear, exponential, and quadratic functions. So that's why we did this, because we're going to be looking at curved situations. So quick review, linear has really two major forms, the slope-intercept form and the standard form for the equation of a line. You should be very familiar with linear equations at this point. Anyway, here's one example, graph to make a straight line. We're going to be focused more on exponential and quadratic equations for the rest of the year, and largely quadratics. But here's the standard form for an exponential equation. Y is equal a times b to the x. In this case, I put the b to the x in parentheses because in situations like this, if you don't put it in parentheses, for example, this would consider it, a computer or calculator would consider that a 32. You can see right here, it's very, very close to zero, and it goes up, 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 up. This is a situation of exponential growth. The form for a quadratic equation is y equals ax squared plus bx plus c. And here's an example right here. And as you can see, this makes a parabola. We're going to be talking a lot more about quadratics and parabolas. We're going to talk about a vertex. We're going to talk about x-intercepts. In this case, there are no x-intercepts, but that is coming soon. All right, the next situation here are just some examples of exponential equations. Note, this one kind of starts at the zero, but then goes downward instead of up. So that's actually a type of equation that we'll be talking about in the next unit. But that is still an example of an exponential equation. Note that the x variable is an exponent. That's the case with all of these. Here's another situation of exponential growth. Y equals 0.2 times 4 to the x. Yeah, this one right here, y equals 0.5 to the x, you can consider the a1 in this situation. This is what we call exponential decay. It starts very high and then goes very low. All right, so this one's exponential growth. This one's exponential decay, and again, we'll do a little bit of work on that in the next unit. Here are some examples of other quadratic equations. Note this is a parabola, but it's facing downward. So y is equal to negative 4x squared plus 9. So you've probably already figured out that negative has something to do with it. Here's a couple of situations where we have x cubed in the equation. And note that just does some kind of cool things here. This has a positive 3 in front of it. This has a negative 2. So that might have something to do with the way these are going. But anyway, there's a quick review of quadratic and exponential formulas. The reason that we reviewed that is we're going to use exponential regression formulas and quadratic regression formulas. So I might call them equations too, same idea. All right, so let's take a look at this. All right, the best way to do this, I think, is to delve right in. So this first problem here is a situation where Top It Off Incorporated is having to make a number of lids for a variety of their containers. So I'll just keep reading this. Some of the most popular lids they produce are circular lids for oil drums and other cylindrical containers. Although the lids are ordered by the diameter of the circle, the price is set by the amount of metal used. All right, so I'm thinking right away we're talking area of a circle. Pi times radius squared. Interesting. All right, Top It Off needs to set up a price structure that relates the weight of the lid to its diameter. Below is a list of weights for the standard size lids currently produced. Okay, so we're going to actually take this data, and I have it all loaded in here, right? And I've actually already got a few things graphed. You know what I'm going to do? I'm going to take them away. All right, so let's just leave this one first. So what I have here is the LSRL, so the least squares regression line, or line of regression. So I've already put this in here, and you can see that it's not too bad a fit. Here are my residuals, my residual plot. It's a little bit curved, but not much. What we're going to do though is see if there's not maybe just a little bit better fit. All right, so for this one, we're going to put in the quadratic regression equation and see what happens. All right, so the quadratic regression equation is y1 is approximately equal to, so it's a x1 squared, so I'm just doing caret 2 for that, plus b, again x1, that's cool, isn't it, plus c. All right, so there we go. So that's the purple line, and I think you can see if you look at that, it's a little bit better fit, just a little bit, slight, but it is a bit better fit than the straight line, right? And then if you look at the residual plots on this is the green ones. Again, not much of a difference, but definitely closer to the 0 than the blue. I'm sorry, than the red. Also, if you look at R squared here, it's 99.58%. This one's a little bit better at 99.86%. Right, the point here is learning that you can put in other equations other than a linear equation. So we used a quadratic for that one. All right, so that really covers the material for problem 105 and 106. I'd like to look now at model 107. Right, so this is Julia's father. Remember, he had a restaurant. I don't think we did this problem, but he uses dry ice to keep glasses in his restaurant quite cold. And the dry ice sublimates, as shown in the table at the right. So if you've not ever heard of the word sublimate, that is when matter goes from a solid directly to a gas. It doesn't have a liquid state. So dry ice is solid carbon dioxide. And that's a really cool thing about dry ice is it sublimates. So we ship meat in it and all that type of thing because ice doesn't melt, just becomes a gas. All right, so we're going to use the Desmos graphing calculator here to take a look at things. I've already put in a few lines. Basically, the green line is actually going to be the least squares line of regression. And then down here, we've typed this in. I'm going to get rid of it and type it in again, right? In this situation, we're going to try typing in an exponential regression line, right? So here's what that looks like. So y1 is approximately equal to a times b, then I'm going to put the caret in again, to the x1, right? And again, you can see if you're looking at the green line versus the blue line is a slightly better fit. R squared in this case is 99.84. R squared in this case is 99.58. So again, in this case, it is slight, but the exponential regression equation is a better fit, right? So down here, if you didn't notice, this happened with the quadratic as well. They'll give you the numbers down here for A and B, so you can actually get the formula. So I'd probably round things, but A is equal to 15.3735, so 15.3735 times 0.959492 to the x power. So again, Desmos allows you to get the equations for both of these. All right, so we've done one with quadratic regression equation and then one with an exponential regression equation. All right, so let's look down here. 608 and 609 go together. This is a situation where we're talking about the amount of oil produced. All right, so right here they have from 1905 to 1972. They're just letting you know MMBBL stands for millions of barrels, and it's the standard abbreviation used by the oil industry. Having a lot of interesting times with the oil industry lately. If you haven't been paying attention to gas prices, they're quite low. All right, enough of that though. All right, so what we've done, and I've actually put this data in here already, so I think I've got it right here. I want you to notice that I took the 19 off each of these. I just did that because the book does it, but it does make sense. All right, so this one to me looks more, it definitely does not look linear. So this one's more obvious. So let's go ahead and put in the linear regression model, right? So mx1 plus b, and you can see real clearly that is a terrible fit, right? And if we do the residual plot on this, that's very clearly like, wow, that's not cool. So it's making a curve itself. All right, for this one, I'm going to go ahead and put in both the quadratic and the exponential, and we'll see what happens. Okay, we just know the linear is not going to work out well. All right, so we've got y1. So I'm going to put in the exponential first. AB to the x1. Okay, so that is my exponential, right? And if I'm looking at r squared here, it's 0.9981. So I'd be looking on the quadratic for something even better than that. So let's try the quadratic. So that's going to be a x1 to the second power plus bx. Gotta remember the 1. Let's see. All right, so this one is the quadratic, and I really don't think that the quadratic is at all correct here. So you can see it goes through a few of them, but that's just not any good. So you know what? I'm going to get rid of that one. All right, clearly the best fit is the exponential, and we can see that just by looking at the line. All right, so and let's plot our residuals. Oh, the residuals have already been plotted. All right, so again, that there was a real clear best fit in this case, definitely a little bit more drastic than the others. All right, what I'm going to do next is I want to go down to 109. In 109, they added some data from 1974 to 1996. All right, so things changed in those years. So what we're going to do is we're going to take a look at this tool in Desmos, right? And then we're going to take a look and see, well, what does the pattern look like here? So you can see in this case, the data from 1974 to 1996 is here, right? But what we're going to do, and if you look right up until 80, it kind of looks like it's following the same pattern. So we've got this data here, right? But then once you start at 82, which is this here, things look a little different, don't they? Right? If you're thinking they look a little more linear, then I would agree with you. All right, so what we're going to do is make the data from 82 to 96 a different color. So we're going to make that red. So in this one, it definitely looks more linear. So what we're going to do is we're going to put in the regression line here. Okay, now watch what I do. This time I'm going to put in Y3, not Y1. People have asked me before, why do we have to put in the subscript? Here's why. We've got a different table here. So this table is X3 and Y3, so we're using the appropriate subscript in the equation. All right, so Y3 is approximately equal to MX3 plus B. All right, and you can see that for just this red part here, that actually does follow quite well. And if you do the residual plot over here, you can see it's pretty close to the line. It's a little up and down, but R squared is basically 98.46%. And if you look at the correlation coefficient also, that's very close to 1.99. So that's a good fit. All right, so here's the thing. Here's the point of this right here, right? So what happens here is there's two different types of models that fit, right? So right here it says we need to take a look at making a piecewise graph that shows both models. All right, so a piecewise graph is like this. It's got a curved model here and it's got a linear model here. All it means is there's two different patterns in the same situation. We will be looking at piecewise graphs in the next unit as well. All right, hey everybody, nice job on statistics. All right, thank you very much, and that is the end.